Welcome to the fourth class in particle fundamentals and fuzzy logic. So just to give you a better idea of the types of setups we're going to be doing now, any 3D object that moves organically would really have three sets of rotations. So it's the one we did in the previous class, which is more or less the left and right direction. Then it's going to have an up and down direction. That's probably going to be fairly different than the left and right direction. And then finally, it's going to have a tilt. So definitely something as streamlined and aerodynamic as a shark is going to do those things very differently. And I think most life forms do those things pretty differently, unless you're like a jellyfish or something. So here, you've got the particle target. And you can see that the direction is going to adapt, and it's not really a separate thing from the other axes. And because we're going to do a lot of repetitive operations, it's good if we modularize our tools a little bit. So the entire example last class, it could really be turned into one tool. And I've coined this tool fuzzy turn degrees, and we're just going to make that really quickly. And then we can use it in quite a few different places for the other axes. The other thing is the actual rotation process. So there's no real reason to repeat the transform and the rotate and things like that over again. So let's just set that up really quickly. I'd advise that with anything in such a low level paradigm is once you're doing something more than once, it's a good idea to turn it into a digital asset and modularize it in maybe a crowd simulation package. This would be called like a brain chunk or something. Let's turn the previous process into a set of more simplistic tools that we can use. All right, so big mess here. And what's this thing really doing? Well, here's where we actually rotated it. So let's go ahead and turn this whole process. We're definitely going to want to repeat the degrees to radians. We can always just feed it in degrees. Let's see, we're probably going to want to rotate any vector, so we'll leave the normalize out. And the up, we're always going to want to normalize that. Otherwise, it'll increase the spin intensity. All right, so this whole process that actually does the rotation, I can call that rotate. And I've already gone and made a digital asset for this. So that would be rotate vector by degrees. Okay, so here's the degrees. This would be the vector that I would like to rotate. And the axis to rotate about would be here. There we go. All right. And let's just connect that to the shark direction. Moving on, it's going to be a really repetitive operation to get the degrees between two angles, and we can use that for all of our tolerances. So here, I've simply made a digital asset, the angle. We can see it's the exact same thing, a simple set of nodes, but it's good not to clutter the networks. So here's vector number 1. Vector number 2, there we are. Okay. And now we really want to clean up this stuff a little bit more. So let's take out the adaptation for just a second. So now let's encapsulate this in a much larger sweep. So we want to take two vectors. So in this case, the shark direction is the vector 1. And we'll actually go through the process of making this digital asset. So this would be a vector should be the rotate vector. All right, and then we'd have the target vector. Okay, so that would be probably our first two inputs. And then we definitely want to normalize both of those. And this would be our angle that would feed into our fuzzy curve. We also want to find the sine. So for that, we would need the third axis, the up. So I'm going to put that out here, and let's call this rotation axis. Okay, so that would be the process of crossing the first two vectors, normalizing that, getting the dot product. Actually, we can just use the sign here. And this would be the which way it should rotate, either to the left, to the right, according to the vector. So that can be a subnetwork, and that I've already gone ahead and made. Let's see, turn sign, here we go. So current direction, target direction, rotation axis. There's our turn sign. Okay. I just made that the opposite, less than 0. Okay, so here's the direction it should turn. And now in comes the rotation degrees. We're multiplying by the time increment, so that's a pretty straightforward thing to encapsulate. This is our maximum turn degrees. Here's our ramp. Okay, almost subnetwork ready here. Okay, so out of all this, what we're really seeking is the output degrees. This rotate is probably common enough to where it's going to be an independent operation, and we might want to do more things after that. So we're really just after this final degrees here. Okay, so let's get this guy out of here. And now let's make this whole thing a digital asset. Create digital asset. We'll call this live fuzzy rotate degrees. And let's just save that to embedded. So notice that this, as this digital asset was made, it's given us a few parameters already. And let's just go ahead and rename those. I'm just going to reference the one I've already made here. So my fuzzy turn degrees. Okay, so this one would be called current direction, because that's really the current vector that's being fed in. Next, we'd want the target direction. Okay, And then finally, spin axis. Okay, now notice that when I'm plugging these things in, they're not actually graying out on the interface. So that in a VOPS digital asset is over here in the input and output. We just have to call these the same thing. Let's apply that. Okay, so now that functions quite nicely. It's working like a real tool. Okay, we would also want any other important things exposed, such as the detection, the maximum angle it should be, as well as the maximum turn degrees. So diving in here, okay, so we want this guy. So the rotation degrees, so let's make a new parameter here. Call that turn strength. Turn strength. And now let's make the other one too. Okay, so here's the rotation degrees will be how strong the turn is. So I'm going to plug that into here. And then this detection degrees that feeds into the fuzzy curve. And it's going to be here. Okay, there we go. And with any luck, this will greatly simplify our setup. However, we want to spit out the degrees to turn and not the actual rotate. So let's actually just put the rotate outside. Okay, so our vector is shark direction, our axis is the shark up. The degrees would be this. I've just added a pivot in case we're rotating about something else. It's just being subtracted before the original vector is made, but if it just defaults to 0. And we're exporting that as the shark direction too. So let's see if that's relatively sane. One thing I should also mention is that we're really just negating or keeping the degrees that we're turning. So we can use the sign directly to multiply. We don't have to go through this if statement. So I'm just going to multiply the result of the curve with the sign with the time increment. and that simplifies the interface a bit more. There we are, that looks a little cleaner. Okay, so because it's only able to turn about its up direction, it's only able to, it's not able to adapt its up and down yet. Okay, so we'll keep this around, and that just should give you an idea of how to modularize the process of all these complex vector operations. It'll really speed up our workflow. So now let's put together the next two operations, the up and down and the tilt. I've gone ahead and adjusted the settings a little bit here, just so it adapts it in a bit more responsive way. There we go. Maybe slow it down a bit. Okay, and now let's repeat that process with a few minor variations for the up and down direction. So for the default shark direction, I'm going to turn this direction off for now just so we can test a little better. Okay, so let's just unplug this. Okay, and then up in the geometry level, I just want to hard code this direction to face down the x-axis for testing purposes. So we'll call this shark direction. I'm just going to add an attribute, and it'll start off facing down the x direction. There we go. And now we want to adjust if it's looking upwards or downwards. So here it should adapt and it should look downwards. Okay, so it's going to be a similar process. This time we actually don't have the axis that we're going to spin on. So we have the up direction and we have the shark direction, but we don't have that third axis that we're going to tilt up and down on. So for that, I'm just going to start off with the subnetwork, and let's get those two axes. The shark direction and the shark up. And let's make the third axis. So this might require a bit of testing. So I think it's important to have a good visualizer. So let's make a few tests. Test A, test B, etc. As many as we need. So to get that third axis, we're going to use the cross product. Okay, let's view that. And let's make this red. Okay, so this is going to be the axis that it can rotate upwards and downwards on. All right, so at this point, it should be fairly similar. We want to rotate it along this axis. If it's downward in one direction, along the opposite axis if it's up. So we can repeat the previous steps we did, and that's where the live fuzzy rotation degrees asset we just made comes in. Okay, and let's normalize this as well. Okay, so this is our rotation axis. And now, okay, so what we want to rotate about, this would be the spin axis. Our current direction, okay, so that's still the shark direction. We want to rotate the shark direction up and down, as well as the shark up. Okay, so we're going to start with the shark direction, rotating that. Let's view the shark direction. And up. Okay, so it's the purple one. All right, and what is the target direction that we're trying to get to? Well, the target direction is still our target vector, right? However, that's with one major difference. If we just have the target vector going in any which direction, then it's going to be rotating very chaotically along this axis. We really want to be specific. We really just want it to rotate in the planar between the up and the shark direction. So what do? Well, it's a very common vector technique to want to flatten a vector along another vector. So for that, we can do two cross products. So we really just want this purple thing to align to the target vector, in this case, to align with this grid. And here it is already. Here it is. But if we were to, say, adjust our direction a little bit, okay, then this wouldn't really be rotating along that axis anymore. Okay, so let's import our target vector. Okay, so in comes the target vector. And let's preview that with a test B. Okay. Okay, so in comes target vector. And here we can see that the target vector in order to rotate this purple line about this axis to this, it's going to change based on the angle. It's going to be different every time the shark is a bit offset, and we can guarantee it's never going to be aligned. So let's pre-align it with two cross products. Okay, so here we'll do a first cross product, and we want to cross this yellow vector with our newly created rotation axis. Okay, so that's going to be crossed, and we're going to have the plane between this red and this yellow, and you can see what that looks like. Okay, and now we're in a position to make something that's aligned with the direction that this can actually rotate. So here we can cross our rotation axis and this yellow vector, and that will create the one we're after. Okay, so another cross product. So we're going to cross this new vector with the rotation axis. Okay, and now it's actually aligned, and we can see that it's aligned in the direction that it should be rotating according to the green and the purple. And you also might notice that it's flipped, and so that is a problem, because here it's going to give us a very different set of degrees based on kind of the trajectory of the shark, and that's artificial. We always just want it to seek to the closest degree it possibly can. So for that, we're probably going to want to refract it about the up if we detect that it's longer than a certain amount of degrees. Okay, well first, since this two cross product thing is so common, let's turn that into a modular asset as well. So I've done that. I've called it flatten on axis. Okay, so here's our target vector, and here's our axis, and it just goes through that same process. Okay, in this case, it's a different order of the cross products, but let's say it wasn't. So let's just switch our cross products here temporarily. Okay, so it's the wrong way now, depending on which side it's on. So what do? And for this, we'll pick the world up. So here's the refract. Even though these two nodes, reflect and refract, might be mostly used for rendering, they're really useful for a lot of things, and I think they're kind of buried and underused. So yeah, here I want to say, okay, if you're this way and you're going to rotate all the way around to get here, instead of just rotating up to here, which is what I want it to do. I don't want it to rotate all the way around to get there and be upside down when all I want it to do is just kind of go up a little bit. So it really should be kind of functioning as both things. So here it's a negative dot product. So we'd want to essentially do this, where we feed in the direction. We want to refract on the y-axis with an index of -1. And now we're basically just bouncing it across this green axis to there. Okay, and we only want to do that if it's if the dot product isn't if the dot product is not positive. So for this, we can use the dot product. We want to get the dot product between the target axis and the shark direction. And if this happens to be negative, then we're just going to switch. So let's do a two-way switch and a compare. If this dot product is less than 0, then refract. Otherwise, keep it. Okay, so now we have our final rotation vector. We're using these two vectors to get the third red vector, and based on the way this should be turning, it's going to rotate now to seek from this to this. It's going to seek that in the similar way as our previous system, our fuzzy rotate degrees system. Okay, so let's match that. Okay, so we flattened it on the axis. Let's make this refract if long way instead of the short way. Okay, so now we have the final target rotation vector. Okay, so this is going to feed into our target direction. We could probably normalize this guy too while we're at it. Okay. So here's our target. Here's our current shark direction. Our spin axis is this red one, the rotation axis. Okay, and let's just set this up the same way we have before. So this digital asset gave us the settings at the particle level. So let's make some parameters for that. I'll call this maximum detect degrees. Okay. And let's call this turn degrees. Turn degrees. Okay. So maximum detection degrees, well, maybe let's shoot for around 30 degrees. And the turning intensity, it should definitely be slower than our left and right direction. So if this left and right direction is 130 degrees per second, let's maybe make that, I don't know, like 80 or 70. Okay, so we've got that. And now let's actually rotate. So rotate vector by degrees. Okay, so here's our Here's our degrees. 0 for the pivot because we're just dealing with vectors. We're going to want to rotate our shark direction along the axis of the rotation axis we computed. Okay, and now let's export the shark direction. Use this node when input is connected, and let's connect that. And lo and behold, we see that we have an adapting shark. And notice it's not actually spinning all the way around. It's only going to go up and down because of this refraction. See, it's still aligned, and we can rely on the other direction to spin it. Pretty cool, huh? So now we can see that as we apply our previous left-right turn direction, okay, we want it actually to turn at this point. What's it going to do? Okay, well, it definitely aligned to that. Okay, and now it's going to choose the most efficient direction on 2 axes and give a much more natural set of adjustments. The only thing that's left to do here is the fact that we're not actually adjusting the up, but the up should be, this should always be a right angle. Okay, so the purple one and the yellow one should always be a right angle. So let's also rotate the up vector as well. And to do that, to guarantee it's a right angle, we wouldn't just want to arbitrarily rotate both of them. So I just want to use that cross product in order to align it. I want to essentially do the same thing. I want to do 2 cross products and flatten this to always make this a 90-degree angle. So to provide the finishing touches there, let's make another feedback loop, and this time with the shark up. Okay, so here's the shark up. Oh, I do want to normalize the shark direction going out. Okay, so shark up, reading in. Let's make a copy, use this node, export when input is connected, form your feedback loop, and then we just want to flatten it about this axis. So we can use the same 2 cross product trick we've done earlier, cross product, and flatten it. And now it should always be a right angle. It should always be aligned to this axis. See how it's always 90 degrees now? Now the only issue we're now seeing is that we have some tilting issues. So in the next lesson, we're going to look at the tilting as well as some banking behavior.